In the previous lectures, we introduced the natural exponential functions and the natural logarithmic functions. We pretty much redefined them based on the integral of 1 over t dt. Now I'm going to define the general exponential function and logarithmic functions based on the natural exponential and natural logarithmic functions. So essentially, we already have y equals e to the x and y equals ln x, which is log base e of x, defined. And we're going to extend it to any base for both exponential and logarithmic function. So the real definition is we define b to the x as a natural log, a natural exponential function e to the x ln(b). I don't want you to worry about the definition too much. Let's just say that it is our old definition in the sense it still do what we know exponential functions are doing. Let's say b squared is still b times b, and b to the first power is still b. And we also have all these nice properties holds. Okay, product of powers, you add the exponents. Quotient of powers, you subtract the exponent. Power of power, you multiply the exponents. And when you have a power of product, it equals the product of powers. Okay, so again, everything that we knew were true stays true. Now we have two new rules about the derivative and the integral. So first of all, the derivative. By our definition, b to the x equals e to the power x ln b. So the derivative b to the x will be, by definition, actually e x ln b. So we are going to use chain rule, and this is where my variable sit. In the formula, it's supposed to be e to the x, so it's e to the whatever the exponent's supposed to be, followed by, since it's not pure x, the derivative of where x is supposed to sit. And this gives me e x ln b times the derivative of x ln b will just be ln b. But remember, this actually is our b to the x. So we had ln b times b to the x. Okay, that's how this is true. And similarly, you can easily see that the integral of b to the x equals 1 over ln b times b to the x plus c, because when you multiply 1 over ln b, so do I really want to do it? I'll quickly do it. So you want the derivative to be just the b to the x. So we divide that 1 over, divide ln b on both hand sides. Then it becomes the integral. Okay, plus c. So the integral of the antiderivative of b to the x is, well, 1 over ln b times the exponential function b to the x itself, and since we're having antiderivative, it's up to a constant with plus c. So these are the two new formulas. When the base is not the e, you have an ln natural log of the base as a factor when you differentiate, and you have its reciprocal when you take integral. First example, I actually want you to observe when you use the exponential rule and when you use the power rule. It depends on where the x, your independent variable, sit. If your independent variable actually sits on the exponent, you are having an exponential function. If your independent variable actually sits in the base, you have a power. So the first example, I want you to differentiate both, but the first one, y equals 10 to sine x, right? So your variable is here. That means you are really having 10 to the sort of x power, but of course x is u. Then we know that dy dx, it's an exponential function. You get ln of the base times the power itself. Since what sits on the exponent is not pure x, you need to follow by the derivative of the exponent. That gives me ln 10 times 10 to the exponent sine x times the derivative of sine x is cosine x. So, well, that's the answer. It's just a huge product. But on the other hand, I have y equals sine x to the 10th power, and my variable sits in the base. So I'm actually having the power rule. I'm having x to the 10th power. And the derivative will be, I pull the exponent to the front, I lower the exponent by 1, and then since the base is not a pure x, followed by its derivative. So 10 sine 9x, sine x to the 9th power, then times cosine x. That is the derivative. And here I want you again to observe the difference. Where when x sits on the exponent, you have exponential function. When x actually belongs to the base, you have a power rule. Okay. Next example, we are finding the antiderivative of 3 to the 2x. So we have b to the x, which means I'm going to use substitute rule where this will be my u. So you have another new candidate for your u, the exponent. So again, u is pretty much where the x's sit in the formula, right? So I'll let u to be 2x. That will be gone. Then I need to deal with my dx. du dx is 2. That means the x is 1/2 du. Then I can rewrite the whole thing equals 3 remains the same, 2x is u now, and dx is 1/2 du. So I'm having 1/2 the integral of 3 to the u's power du, where I apply the integral of b to the x dx. I keep my 1/2, I take the reciprocal of ln of the base. Then I keep the same exponent and power plus c. I didn't have a u, so I need to write the u as what it is, 2x plus c. So it's 1 over 2 ln 3 times 3 to the 2x power plus c. Or if you want to make it look nicer as a form, combine, multiply the two factors into one fraction. These are just basic direct application of applying the formulas. Okay, now you can try practice number 1 and number 2. We talk about when the variable sits in the base, we use power rule. When the variable sits on the exponent, we use exponential function. But what if you have x in both the base and the exponent, f of x, g of x? Okay, so when you have the variable in both, there are two ways you can deal with it. The first way, you call it y, and then you do the ln on both hand sides, so that you bring down the exponent. Or now you have another way, you can just rewrite the power in base e, and then the exponent will be ln, which of the original power, which also bring down the exponent. So both way works. Personally, I prefer the second way because I don't have to rewrite and do the differentiation on both hand sides to get 1 over y dy dx. But both way works. Pick the one that you like. I'll do both here. So first way, I will just take ln on both hand sides. Ln y equals ln x radical, oops, that's the exponent, x. This is square root of x, ln x. Then I'll differentiate both hand sides with respect to x. So for ln y, I use chain rule. Derivative of ln gives you 1 over the input, but meanwhile, y is a function of x. On the right hand side, I'm differentiating this, or x 1/2. No, I don't have room, so I'll keep it this way. So this x to 1/2 power times the derivative of ln, which is 1 over x, plus, well, maybe let me slow down. I'm having square root of x times ln x derivative plus ln x times square root of x derivative. This is x 1/2 times 1 over x plus ln x times 1/2 square root of x. So this gives me 1 over square root of x plus ln x over 2 square root of x, or 2 square root of x. On the bottom, I multiply by 2 here and here, 2 plus ln x. Finally, my dy dx equals y times the 2 plus ln x over 2 square root of x, where y is x to the power root of x, 2 plus ln x over 2 radical x. These are all computations, but the key here is you take ln on both hand sides so that you can bring down the exponent to the sort of the base level. The second way, we know that exponential function and logarithmic functions are inverse of each other, so y, which is x to the power of x, is also e ln of the same thing, x radical, on the exponent. Then I keep the e and I bring my exponent of a log to the front, radical x ln x. Then I just differentiate it and use chain rule. The derivative of e to the x is e to the x, but where it's supposed to be x sits this huge product, so followed by the derivative of this product, and that is e radical x ln x times radical x times 1/2, 1 over x plus ln x times the derivative of square root of x. I'll cheat here. You can do that. So e square root of x ln x. Then here I'm having 1 over radical x plus ln x over 2 radical x. But remember, this thing was y, or x square root of x. So it's still x to the power of square root of x times 2 radical x, 2 plus ln x. So I get exactly the same answer in 2 different ways. If you don't like to sort of carry a huge thing on the exponent, all the way to the end, you might want to consider take ln on both hand sides. In a way, if you look at the left hand side, it's not direct. You don't get to compute dy dx right away, but meanwhile, you don't have the exponent, the base e and everything on the exponent, issue. But bottom line, both of them work. Just pick the way you like better. Next, we are going to define the general logarithmic function. So we defined general exponential function, and then the logarithmic function will just be their reciprocal, their inverse functions. Okay. Again, all the properties that we knew holds, but in particular, we define the logarithmic function as the inverse of exponential function. So we have the properties of inverse functions, exponential and logarithmic composed. You get identity. So either you do log before exponential or exponential before log. As long as they have the same base, you go back to the input x, the cancellation rules. Then we have log base e of x is ln x. And the third is very important. The third formula is called change of base formula. So for any log, you sort of can view it this way. Log base b of x is ln x over ln b. That's how we defined everything, right, to start with. But also it equals log base a of x over log base a of b. So essentially you cut it this way and you choose any base you want. If you want e as base, perfect, you get ln x, ln b. But if you want to choose another base, you could do that too. Then finally, the derivative of the general logarithmic function will be the derivative of log base b of x. Using the change of base formula, it's actually d dx of ln x over ln b. So I can pull out my ln b and take the derivative of x. That gives me 1 over x. 1 over ln bx. So when you are differentiate a general logarithmic function on top of the 1 over x, you get again a reciprocal of ln b. I think it's quite natural when you get a general logarithmic function, a logarithmic function with another base. Just change the base. Okay, so whatever comes out as the denominator, you pull it out and you deal with the natural log that we all know by now. Next is a remark. The number e actually is very, very important in mathematics. So here, actually, we are able to express e as a very important limit. So this is 1 plus x. When x gets very, very small, 1 plus x is essentially 1. But meanwhile, 1 over x becomes like infinity. So this is like a sort of a number very close to 1, multiplied by close to 1 but greater than 1, multiplied by itself so many times. So it becomes a little bit bigger. How much bigger? Actually, e. Okay, there are a lot of ways you can express e as limit. This is one of the examples. Finally, let's differentiate a general logarithmic function. So y equals log base 10 of square root of x. So this is common log. But anyway, it's log base 10. dy dx. Well, sorry. Before I get to the derivative, as I said, when you have common log, when you have log other than ln, convert it. This is ln square root of x over ln 10. And when you have square root, you can even pull that out, 1/2 ln x over ln 10. Or 1 over 2 ln 10 times ln x. So you prepare the original function so that when you take derivative, it's just you take the coefficient out and then you take the derivative of ln x, which is 1 over 2 ln 10. The derivative of ln x, of course, is 1 over x. So finally, I have still 1 for numerator, but a huge denominator 2, ln 10, then x. So when you are dealing with a general logarithmic function, just use change of base formula, change everything in terms of ln, so that you have a neat derivative and you have a neat integral. Whatever you do, it will be nicer than every time you differentiate or you integral, you get a log of the base. Okay, that's it for this lecture, and you can finish the practice number 5 and 6.